So, in this lecture we will talk about a completely different topic. In the previous lectures we discussed on structures of ceramics, what are the fundamental basis on which ceramic structures are formed, and we discussed various type of ceramic structures like FCC based structures, HCP based structures and other structures such as cubic packing of anions, etc. In this lecture we will start with defect chemistry of these ceramic materials. Now, defect chemistry is very important from the point of view of properties, because none of these ceramics are perfect in nature, that is, they contain defects which are equilibrium in nature, which are thermodynamically stable, and we need to understand how these defects are formed, under what conditions, what kind of defects are stable, which would help us in understanding the property evolution in these ceramics. So, the first topic, so the name of this module I would put it as. So, first we will look at defect chemistry, followed by defect equilibria. So, these are the two topics that we will discuss in this module. Defect chemistry deals with thermodynamics of defect formation as well as defects, the various kind of defects, etc. Defect equilibrium is under various conditions of atmosphere, etc., what kind of defects are stable under equilibrium. So, this also talks about thermodynamics. So, to begin with, there are various kind of defects that are available and that are present in ceramic materials or other materials as well. You can have dislocations which are one dimensional defects, you can have grain boundaries, you can have various other kind of surfaces, twins, etc. But here we are mainly concerned with defects which are point defects, which are 0 dimensional defects, and which are also called which are basically vacancies or interstitials. Now, in contrast to metals, the vacancy or interstitials in ionic solids or ceramics are entities which contain charges, since you have the presence of oppositely charged ions. As a result, to maintain the stoichiometry as well as charge stability, charge neutrality, these defects tend to be charged, and which makes them pretty special. So basically we are interested in learning about point defects, and these defects are basically deviation from the perfect atomic arrangement in a perfect solid, and these can be called as vacancies, which are atoms or atoms is missing from their positions. It could be interstitials, interstitials are typically a foreign atom, or it could be a host atom sitting inside an interstitial site, and you know what interstitial site is after a discussion in lecture 1 module 1. It could be substitutional ions. So, you can have an impurity which substitutes for the host atom. You can have presence of valence electrons as well as holes. So, all these make point defects which are interesting from the point of view of property determination in these solids. Point defects in metals tend to be electrically neutral, simply because you have only one kind of atom present there, whereas in ceramics, which are typically ionic materials, these tend to be electrically charged. So, we can define further point defects into two categories. The first category could be ionic defects, and in terms of ionic defects, these are the ones which occupy lattice positions, which are the regular positions, and they can be either this or that or that. So, if I say number 1, number 2, number 3 and number 4, then either of 1, 2 and 3, and you can have electronic defects, these are basically created due to deviation from the ground state electron orbit configuration. So, these typically you can think of, if since these ionic solids have a band gap, as we will see later on, since these are, their band gap is above in most cases 2 electron volt, 2.5 electron volt. The electrons from the valence band get excited into the conduction band due to either thermal means or any other means, which means this gives rise to creation of electron and hole pairs. So, now we will look at first some of the conventions. The conventions for since the defects are charged, there are certain conventions, and these conventions are known as we define them as Kroger-Wink notations. So, let us say example is an oxide MO. So, where metal is a bivalent cation. So, if you have metal ion on regular site, it is known as M subscript M. So, this is how a regular metal ion will be. Similarly, oxygen ion on regular site will be given as OO, or if you had a cation X, anion X, then it would be XX. And then you have host of these point defects. So, for example, a metal vacancy is represented as Vm, and if it is, so if you have a neutral vacancy, the vacancy which does not contain any charge, it will be Vmx, or if it is charged, then it would be Vm dash, or if it is completely charged, as in case of a metal oxide with the divalent metal cation, it would be maximum negatively charged with 2 negative charges. So, this would be when the vacancy is completely ionized, and these are the states when vacancy is not completely ionized. Similarly, an oxygen vacancy is written as VO. A neutral oxygen vacancy will be VOX, singly charged oxygen vacancy will be VO dot, or completely charged oxygen vacancy would be VO double dot. So, double dot will represent 2 positive charges, double dash will mean 2 negative charges. And if you have oxygen interstitial, which means oxygen going to an interstitial site, this would be OI, and if it is completely charged, it would be OI dash dash. And if you have a metal interstitial, this would be MI, and if it is completely ionized, it would be MI double dash. So, we are taking, so all these number of charges, all these number of dashes or dots represent for an oxide MO. So, if you have MO2 or M2O or M2O3, M2O5, the number of dots and dashes will change for metal cation. For oxygen, it will remain same. Okay. So, and a foreign metal ion, it would be represented as MF, MFM. Okay. So, foreign metal ion on metal side, which is the regular metal site. Okay. So, this would be regular metal site. So, if the oxide was MO, so you have this foreign metal ion MF, MF going to regular M site will make it as MFM, and number of dashes here will depend upon the charges which are carried by foreign metal ion. So, for instance, if you have let us say we had let us say A2O3 in BO. So, I am not writing the complete reaction, I am just writing if A goes to M site. So, this would be AB, and in this case since A contains plus 3 charges and B contains plus 2 charges, it would be as a result net plus 1. So, this is the example. Okay. And vice versa, if you have A2O in BO, then it would contain 1 negative charge. So, the number of dashes or dots will depend upon the type of substitutional for an atom. And so, this is foreign metal on regular metal site. If you have foreign cation on interstitial site, it would be known as MFI. So, basically either here MF or either here MF basically means a foreign metal ion. You can denote it as A or B or whatever you like, just to simplify it. And for electrons and holes, it is E dash or H dot. So, basically one dot is positive charge, single positive charge, and one dash represents okay. So, this is the convention which we have to follow when we are going to do this defect chemistry exercise for all these defects. So, now the second thing is second most important thing is how to write these defect reactions. Now, these defects are formed, and you have to at least believe me that they are stable. We will prove the thermodynamic basis in a little while, and they are stable. So, the formation of these defects can be represented via reactions like chemical reactions, and these are called as defect reactions. So, there are certain rules for writing these defect reactions, and these rules are, so you have defect reactions, and there are certain rules for writing defect reaction. The first rule is site balance is maintained, which means number of metal site to number of oxygen site or anion site is always maintained according to the chemical formula. Mass balance is preserved, and then you have to maintain the electrical neutrality. The system on the whole after writing the defect reaction has to remain in electrically neutral state. So, electrical neutrality to be preserved, and we can do a thermodynamic analysis to work out what is the ionic defect concentration. In the whole exercise that we undertake in this lectures, in these lectures, we will assume that all the defects are completely ionized, which means if you have oxygen vacancy, we will take it as VO dot dot completely ionized, and if you have metal vacancy, and if metal was M2 plus, then this would be Vm dash dash, and this will also means it is completely ionized. So, we will assume complete ionization of these defects while writing these defect reaction, but you have to maintain the site balance, the mass balance and the electrical neutrality. You have to preserve these three things to correctly write these defect reactions, and as unless you write these defect reactions correctly, you cannot calculate the defect concentration and related to thermodynamic parameters accurately. So, this is something which is important. So, first we will consider the cases of defects that are present in stoichiometric solids. So, here we will take in this first we will consider defects in stoichiometric solids. What it means is that the stoichiometric solids will mean the oxides or solid which tend to preserve their chemical integrity. So, if it is MO, it would mean MO, which means for each oxygen atom there is a M present, there is nothing. So, you do not have this disbalance of metal and oxygen in a stoichiometric material. So, if you create a point defect for particular ion, which means a complementary defect for that another ion or that particular site has to be created, so that you maintain the stoichiometric nature of this solid. So, you can have various combinations. You can have combination of a metal vacancy compensated by a oxygen vacancy. You can have a metal interstitial, which means a regular metal ion missing from its site going to interstitial site, but it has to be compensated by a metal vacancy, because site balance in that case has to be maintained. So, it has to be complete package. So, various combinations are possible, and we will take example of some of these cases, and the first of such cases is called as Schottky defect. Or Schottky disorder. So, here when we wrote MO, it would mean stoichiometric. So, in case of Schottky defect, what happens is that typically these defects are normally formed as the outer surface or at the defects such as dislocations or at the inner surfaces. If the defects form inside the crystal, then eventually it diffuses out on the surface, out towards the surface of the crystal until you reach a equilibrium. And this defect is like, so I can draw this defect as, suppose these are the bigger ions, let us say, which are the anions, now if I draw the cation let us say goes here. So, each of these has 4 nearest neighbors. So, this makes MO kind of solid. So, this would be in this case MO oxide. Okay. Now, this is a perfect solid. Now, what happens in a Schottky defect is one of these metal site is missing, and to complement that any of one of these, oxygen site will be missing. So, what it will look like is, so this will be, or sometimes it is also represented as a square, and in this case it would be represented by red square. So, if I denote these, so this would be your oxygen vacancy, and this would be your regular oxygen site, this would be your metal vacancy, and this would be your regular metal site. So, here what you see in a otherwise perfect lattice is creation of a pair of vacancy, out of which one is metal and one is oxygen. So, again you see that that you maintain the site balance for each oxygen site, each metal site is missing, which means the whole stoichiometry of the crystal is maintained. And now, how do you maintain the charges. So, when the way you write this defect reaction is, so the way I write this defect reaction is, I write this defect reaction null, which is equivalent to 0, because the creation of a vacancy pair actually basically leads to nothing, right. So, null leads to V m plus V o. Now, if they were completely charged, V m would be double dash and V o would be double dot. So, this is, or I can write 0. So, this is what is formation of Schottky defect. So, here you can see the charge neutrality is maintained for two charges of metal vacancy which are negative. You have two charges of oxygen vacancy which are positive. Now, the question arises, you must be wondering why these vacancies have charges. Now, you can understand this like suppose you have a metal, you consider this about regular metal side. Now, regular metal side have a metal ion sitting which is +2 in nature, which means the site to which this +2 ion is attracted has to have a charge which is complementary in nature. So, when this metal ion goes away, the resulting vacancy will contain -2 charge. Similarly, same is true about the oxygen vacancy. This is a very simple way of understanding why these vacancies have charges. And these defects are typically present in most of the materials, especially when metal and oxygen are of comparable sizes. So, examples of materials which follow this structure are, so examples are, for example, NaCl, MgO or corundum or rutile, etc., etc. All of these materials, first two are rock salt structure compound, then you have Al2O3, then you have TiO2. So, all of these oxides or compounds are prone to having Schottky defect formation. So, I have written this defect reaction for a binary metal oxide which is MO, whose formula is MO. Now, the defect reaction formula would change for example, Al2O3. In case of Al2O3, how would you write it? In case of Al2O3, it would mean null is equal to 2 VAl. In this case, it would have 3 charges because aluminum is +3 plus 3 VO. So, now if you see the defect reaction, here you have side balance as well as charge balance, and you have maintained the mass balance as well, whatever has. So, you can write mass balance would be, suppose you had this M. Now, Schottky defects are typically formed during the stage of formation itself. So, the regular sites on which you would have metal and oxygen going to, they do not occupy those, and since formation of solid which is nothing but nucleation and growth is a more like a random walk phenomena because of diffusion. As a result, when you write the defect reaction, you say that they start from nothing, and you start from nothing because these sites were anyway empty to begin with and they were not occupied by metal and oxygen. As a result, it is Vm plus Vo. You can also think of this in this way, Mo being Vm plus Vo. Now, M goes out and O goes out. O will of course goes out in the form of half O2, but M, unless the metal is volatile, it will not go out. So, I mean this is not very accurate way of writing, but you can understand this in this fashion as well. So, whatever MO hypothetically that are present there, it has gone out, but since the defect forms during the formation stage itself, the more accurate way of writing is this above line. And if you look at these equations, you have to maintain the side balance, mass balance as well as the charge balance. So, this would be Schottky defect formation in these solids. Now, we will look at the second, another important defect which is present in stoichiometric materials, and its name is, so the second one is Frenkel disorder, Frenkel defect or Frenkel disorder. Now, these Frenkel disorders are defects where a particular ion goes missing from its site, but it does not leave the solid, it is present inside the solid in an interstitial site. So, what happens is you have, again I will draw the structure. So, you have now you again put these okay. So, this would be present in the solids where you have empty interstitial sites. So, for example, this particular ion which is missing from its position, let us say this is the position, this is regular metal site. So, this would be, I would say, MM, and this would be OO. All right. Now, let us say this particular ion goes missing from its site. So, what it has created here is so it has created a vacancy which is Vm, and if example I take of MO, then it would be Vm double dash. Now, how does this gets compensated? You do not have any missing anions. So, site balance is all right, but mass balance is not there. So, where does it go? It goes somewhere in the solid itself. So, let us say it goes in one of the other interstitial sites. So, in this case let us say it goes here. So, this would be your, I will have to color it differently. So, this would be your metal interstitial or Mi, and since it has plus 2 charges, it would be Mi dot dot. So, how do you write the defect reaction? The defect reaction would be again 0. So, what it means is that basically a metal ion which would have been present on its regular site is not there, rather it goes to a empty interstitial site. So, this would be Mi plus Vm. So, here you can see the charge and mass balance as well as the site balance. Now, these defects can form typically inside the crystals, and it generally happens when metal ions are considerably smaller as compared to oxygen ions, because as you can understand, the metal ion has to go to interstitial site and to try to expand the lattice, which means the size of the voids and the metal ions themselves, size of the voids have to be larger than the or at least equivalent or comparable to the size of metal ion, which means the metal ion have to be smaller in nature. And if it happens with the typical examples are halides of silver. So, for example, silver iodide, silver bromide, etc. These follow this kind of structure. So, if it happens with metal interstitial, it is called as Frenkel defect, and if it has happened with oxygen or anion, it is called as anti-Frenkel. So, in case of anti-Frenkel, what will happen is so again site and charge and mass balance have to be maintained. It is just that you replace here in case of Frenkel you have metal vacancy and metal interstitial formation. In case of anti-Frenkel you have oxygen interstitial and oxygen vacancy formation. And the third defect in stoichiometric solids is called as intrinsic ionization. And in this case you have thermal creation of electron and hole pairs. So, basically you have this this is your conduction band, this is your valence band, and this is your band gap, and electrons from valence band jump into the conduction band, giving rise to formation of a electron hole pair. So, this is called as thermal creation of electrons and holes, and the defect reaction is again written as, since electron hole pair combination is 0 charge, it would be formation of electron plus hole. So, this is your intrinsic ionization reaction. Now, these are the cases or most common cases for stoichiometric oxides. Similarly, but oxides are not only stoichiometric, they can also be non-stoichiometric, which means what it means by non-stoichiometry is that, for example, in an oxide MO, you can have excess of oxygen, you can have excess of metal, or you can have vacancy of deficiency of oxygen or deficiency of metal, and these are all stable forms. And in these materials, when they are non-stoichiometric, the defect structures are they depend upon the level of non-stoichiometry. So, let us see how it works in case of non-stoichiometric materials. So, now we will look at defects in non-stoichiometric oxides. We will take examples of oxides, because oxides are first of all examples of ionic materials or electroceramics, and most of the electronic and magnetic ceramics tend to be oxides, and these are the materials which are more prone to having this non-stoichiometry. So, typically of two types. So, first one, you can have oxygen deficient. Oxygen deficient would mean MO1 minus X. What it also means is that it could be metal excess. So, here I can write M1 minus YO. So, metal deficient or oxygen deficient or metal excess are typically in the same category, and the second could be your oxygen excess or metal deficiency. So, oxygen excess would be MO1 plus X or Y or delta, I mean choice of X, Y, Z or delta will depend upon you, and it would be M1 minus YO. So, this is one category and this is another category. These are the two major categories, and the moment you have non-stoichiometry, which means the moment you have excess or deficiency of any particular ion, it requires the presence of point defects, and you cannot avoid that, and the concentration of these defects will be governed by what is the extent of non-stoichiometry. So, here again you have to maintain the electrical neutrality, and electrical neutrality is preserved by either the formation of point defects and electronic charges or oxidation or reduction of the regular metal ions. Typically oxygen does not have multiple valence state, it is typically metals which tend to have multiple valence states. The creation of extra charges has to be taken care either by formation of extra electrons or holes or oxidation or reduction of cations. So, and of course, intrinsic ionization is always a possibility, whether it is stoichiometric or non-stoichiometric material. So, first we will take example of oxygen deficient oxides. Okay. So, in these now I have not written oxygen deficient or metal excess oxides. So, if I write oxygen deficient oxides, it also means metal excess oxides. So, for the sake of clarity, I can write here or metal excess oxides. So, we will take these examples. So, formation of basically oxygen vacancy or metastacial both is likely, and typically formation of these vacancies occurs mainly at the surface. So, let us say case 1, when oxygen vacancies are the dominating defects. Okay. So, here in this case we depict these by the formula. So, the formula is written as MO1 minus X if it was MO, or MO2 minus X if it was MO2, and so on and so forth. So, the overall reaction in this case would be, so if you have, for example, if I take MO2 minus X, so the reaction would be MO2, which is the stoichiometric form. Now, this becomes MO2 minus X plus half O2 multiplied by X. Okay. So, this much oxygen has gone out of the system. Now, what you are left with after what oxygen has gone out of the system, or oxygen is forced to go out of the system, whatever the reason is, due to loss of oxygen, the stoichiometry now is MO2 minus X. So, due to loss of oxygen, what is the state inside the material? So, you can have, so now we can write what is the defect reaction. So, defect reaction, for example, the first case could be electronic compensation. So, if you have electronic compensation, then what it means is that basically MO2 minus X amount of oxygen has gone out, and it gives rise to creation of certain defects. So, in this case we can write the reaction as oxygen at oxygen site. Now, it goes out of the system. So, how it goes out of the system is, let us say it goes out as half O2, giving rise to, naturally if we are saying oxygen vacancies are dominating, giving rise to oxygen vacancies. So, for each oxygen going out you have one oxygen vacancy created. Now, this oxygen vacancy creates two positive charges. Now, what can this positive charge be compensated by? This can be, if I am saying it is electronic compensation, then this is compensated by creation of two electrons. So, these two electrons will contain two negative charges, which will compensate these two positive charges. On the contrary, you can also have another kind of compensation, which is called as ionic compensation. What will happen in this ionic compensation? The oxygen at oxygen site will go out, oxygen is lost, giving rise to oxygen vacancy, but you do not create electrons in this case. Rather, what you do is that you see a reduction in the metal site, which means this creation of two charges will have to be borne by something happening at the metal site. Now, in that case, since oxygen vacancy contains plus two charges, the metal site has to contain two negative charges, but in this case metal is, so metal at metal site. Now, in this case you have plus 4 metal ion. So, plus 4, either the plus 4 metal ions becomes plus 2, or 2 plus 4 sites become plus 3, which means I can write this as 2 mm dash, which means mm dash would in this case means reduction from plus 4 state to plus 3 state, or it can also mean plus mm double dash, which means reduction from +4 to +2 state. However, this first scenario is more likely because it is reduction from +4 to +3 state, since the reduction oxidation happens in subsequent steps. So, the first scenario is more likely as compared to the second scenario. And what decides which of these is going to be present depends upon the oxide entirely and various thermodynamics parameters, as we will see later on in this course at some instance. So, this is the first scenario when oxygen vacancies are the dominating defects. Second scenario could be, so in the first case 1, and here I write as case 2, when metal interstitials dominate. Now, when this happens, in that case we can depict the oxide as first of all M 1 plus Y O2. Okay, so, you have some extra metal there, and Y is X, just like X, where X determined the loss of oxygen. Here this is Y would determine the loss of extent of non-stoichiometry or extent of excess metal. So, again the possible reactions are, first reaction could be your ionic compensation, so ionic compensation basically would lead to, in this case when you have excess metal, the metal tends to go to metal interstitial site. So, what basically you have as a defect reaction is M tends to go to Mi. So, in this case I have taken it as +4. So, it would be Mi 4 dots plus 4 M M. So, what I have done is, the metal has gone to metal interstitial side, giving rise to +4 charges, and those +4 charges are compensated by reduction of 4 metal ions on regular metal sides to +3 state. So, this is ionic compensation, or electronic compensation. Electronic compensation is similar, easy, Mi plus 4 electrons. So, this is the electronic compensation reaction. Another change that you observe in two cases is, in the first case for each oxygen vacancy you created 2 electrons, okay, and here and there was a dependence on partial pressure of oxygen, whereas in this case you have this there is no dependence on partial pressure of oxygen, and you create for each metal interstitial ion you create 4 electrons. So, this is the difference between two reactions, and these electrons which are created in these two cases are called as quasi free electrons, or if there is reduction in that case, then it is often referred as dash. In these solids, again the conduction, since you have quasi electrons present, these electrons can be source of conduction as well in these materials, and as a result of presence of these quasi free electrons, many of these materials tend to be n type conductors. So, typical examples could be n type conductors due to quasi free electrons, and examples are materials like TiO2, ZrO2, CeO2. So, all these AO2 kind of oxides, or you can have materials like Nb2O5, which are also prone to having this kind of defect chemistry. Second defect, second thing about non-stoichiometric oxides is metal deficient oxides, and we will look at the case of metal deficient oxides in the next class. Thank you.